All right, let's jump right in. We're diving into something really fascinating today, a breakthrough in AI that might, just might, be the key to finally teaching our most complex robots how to move with real skill and purpose, the way they do in the movies.
I mean, just think about it for a second. In what feels like the blink of an eye, we've seen AI do these incredible things. It's creating art that's genuinely breathtaking, writing poetry, even writing code for us. The pace of progress, it's just been insane.
But here's the weird thing. All that progress makes for a really strange paradox. If AI is so brilliant, why do we still see these videos of these super expensive, super advanced robots, well, kind of stumbling around like they've had one too many? Why is the physical world so much harder for them to crack than the digital one? That is the big puzzle we're going to try and solve today.
Okay, so let's get into it. The whole clumsy robot problem, it's not about a lack of computing power or not having strong enough motors. Nope. The real villain of the story is this wild concept from mathematics and computer science called the curse of dimensionality.
So what is that? Well, imagine you're in a library, but this isn't a normal library. This one contains a book for every possible combination of letters. You're trying to find Shakespeare, but instead, almost every single book you pull off the shelf is just total, complete gibberish. That's the curse of dimensionality. And for a robot, every single joint, every elbow, knee, or wrist adds a whole new dimension of possibility. That library of potential movements doesn't just get big, it gets, well, astronomically huge.
So get this, the robot in this study has 69 controllable joints. 69! That's what we call a 69-dimensional action space. Now, when the older AI methods try to learn by just randomly trying stuff in a space that massive, they just get completely lost. It's like being adrift in that gibberish library. And the result? They don't learn to walk or punch, they just jitter. The paper calls it meaningless jittering behavior, which is a perfect description.
So, okay, how do you solve that? How do you find that one good book in an infinite library of nonsense? Well, the researchers had this aha moment. The answer is, you don't even try. You totally flip the script. Instead of just wandering around hoping to get lucky, you make a map first. You figure out where the good stuff is before you start looking.
And this quote from the paper, it really nails it. They say the trick is to construct a semantically meaningful skill latent space a priori. Whoa, okay, big words. But what that really means is they build the map first, before the robot even tries to move an inch. So instead of throwing the AI into that giant, chaotic library, they give it a small, curated bookshelf, a little greatest hits collection of movements that they already know are good. And this really breaks down the difference, right? You can see it here. On the one hand, you've got the old way, just wandering around, which ends up in total chaos. But on the other hand, you've got this new method, RGSD. It starts by studying good examples, like motion capture of a person walking. It uses that to build its skill map. And then, only then, does it start exploring. But here's the key. It's not exploring randomly. It's exploring the interesting spaces between the good spots it already knows on the map.
Okay, so how does this map-making idea actually work in practice? Let's meet the hero of our story. It's a method called reference-grounded skill discovery, or RGSD for short. And this is the algorithm that takes that cool concept and makes it real. It all happens in a few stages. First up is pretraining. This is where the AI basically goes to school. It studies a whole library of human motion capture data, people walking, punching, you name it. It uses this technique called contrastive learning, which is just a fancy way of saying it learns to tell what's similar and what's different, and that's how it builds its skill map. Then you've got imitation. This is pretty straightforward. The robot just practices copying those movements it just studied, and it gets rewarded for doing it well. But now, here's where the magic really happens. The final step is discovery. The AI is actually encouraged to explore the gaps, the empty spaces between the skills it's already mastered. It's kind of like a dancer, right? First, you learn the exact steps to the waltz, then the exact steps to the tango. But then, you start improvising, blending them together to create something new. That's what the robot is doing here.
Now, you're going to hear this term latent space thrown around a lot in AI, and honestly, it can sound pretty scary. But don't worry about it. For what we're talking about today, just think of it as that skill map. That's all it is. It's just a way for the AI to organize ideas. So maybe one spot on the map is walk straight ahead, and a spot right next to it might be walk straight ahead but veer a little to the left. Meanwhile, something totally different, like throw a punch, would be way off in a completely different neighborhood on the map.
Okay, so this all sounds really clever in theory.
A skill map, imitation, discovery, it makes sense. But the big question, the only one that really matters, is does it actually work? Well, let's take a look at the results, because honestly, the difference here is pretty staggering.
You know, the numbers don't lie. This table lays it all out, comparing RGSD to some other big-name methods out there. Now, you're looking at Cartesian error, that's basically how accurate the robot is, and motion FID, which is how natural and human-like the movement looks. For both of these, a lower number is way, way better. And, well, you can see it for yourself. RGSD just blows the others out of the water. Its movements are just so much more accurate and so much more natural.
Okay, but this next part, this is what I think is the coolest thing about this whole paper. RGSD didn't just become a perfect copycat, it actually used that skill map to come up with new, useful skills all on its own. For example, the training data only showed it how to sidestep to the right, but the AI figured out, hey, I can probably do this to the left too, and forward, and back. It generalized. It learned to punch at different targets, not just the one it was shown. This is huge. It proves it's not just memorizing a routine, it's actually understanding the idea of what a punch or a sidestep is.
And what's the point of learning a skill if you can't use it, right? So the researchers tested this. They gave the robot a new task, a real goal, sidestep to reach that target. And guess what? RGSD crushed it. It performed just as well as the best methods that only focus on imitation. This is so important because it shows the robot isn't just learning party tricks. It's building a whole library of skills that it can actually pull from to solve new problems it's never seen before.
So let's zoom out for a second. Why should we care about this? It's more than just making some cool-looking robot animations. What we might be looking at here is a complete, fundamental shift in how we teach robots to do, well, anything physical. And the implications of that? They're absolutely massive. Even the authors of the paper don't see this as just one neat trick. They call it a practical recipe. I love that phrasing. It's like they've figured out the basic instructions, the blueprint that could finally let us teach skills to any complex robot, whether it has 20 joints or 200.
And this core idea, imitation for discovery, could be the key that unlocks something huge, a foundation model for physical control. Just think for a second about what models like ChatGPT or GPT-4 did for language, right? You have one giant model trained on tons of data that you can then use for basically anything. Well, this research points towards how we could build a ChatGPT for movement.
And that leaves us with a pretty mind-blown question to chew on. What if we could stop programming every tiny little movement for a robot? What if, one day, we could have a general-purpose robot that learns how to cook a meal, or assemble a piece of furniture, or maybe even assist in a surgery, just by watching a human do it a few times? It sounds like science fiction, but after this research, that future, it feels a whole lot closer.